Hello and welcome to a new problem solving session, and we are going to discuss some kind of oscillations in this video, and they are named as transverse and longitudinal oscillations. I don't know anything about all these things, so let's read the statement of the problem and just go to solve it. The problem statement is a thin light spring, okay, is extended by delta L1. So the spring is already extended, okay, and fixed on a smooth horizontal table at points A and B. You can see there a ratio of the periods of a small transverse and longitudinal oscillations. A ratio of the periods of a small transverse and longitudinal oscillations of a small weight at the spring midpoint, that is placed at the spring midpoint, equals N1 equals 4 after the extension has been increased. Okay, so it has been increased from delta L1 to delta L1 plus delta X, increased by delta X equals 3.5 centimeter. The ratio becomes N2 equals 3. Why, I don't know. Determine the natural length L0 of the spring and the extensions delta L1 and delta L2 in both cases. Assume that the spring obeys Hooke's law. That's right. That's great. But the first thing I can see here that a single spring has been divided into two springs. It has got some kind of cut in the middle of the spring. So if previously its spring constant was K, these parts will have a spring constant equal to 2K because they have been shortened, so they have become more stiff, and their length has been halved, so their spring constant will be doubled. So you can see here two springs, each of a spring constant 2K, and they are already in tension. What can I do? Let us solve this problem for longitudinal oscillation first. And in the first case, the spring length is simply L0 plus delta L1. L0 is the natural length of the spring. So the spring we are dealing with has got the length L0 plus delta L1. And the spring force developed in both the parts of the string after cutting it into two parts. It's simply their lengths. Their lengths have become halved. So the total length was L0, so this length will become L0 by 2, and this will be again, but I don't need to work on these things. I can simply say them that the spring is under some kind of stress already, and this was created by some force F, and this is true in both cases, whether the oscillations are in longitudinal or transverse direction. It doesn't matter. Let's call this force F. And now the spring is already stretched some length, but the ball is placed in the middle, so it will be experiences same force from both sides, so it will be in equilibrium initially. Now, so violate this equilibrium, I need to displace this block a bit, suppose it by a distance x from its equilibrium position, so that this extended spring is going to exert a force due to its previous extension, and that force was simply F, and plus we extended it further by a length x, so this is going to produce another force that will be 2kx, because its spring constant has become 2k now. So the force acting on left due to left spring will be F plus 2kx. X is due to its initial extension. And what about the right spring? Right spring was already extended before doing anything else, when the mass was at the middle of the rod, and in that case it will be producing a force F in this direction. And now we have compressed it by a length x towards right, so it will going to exert some force in opposite direction, that will be 2kx. So these are the forces acting on the ball or a small weight right now, and we can write the equations accordingly since we displaced in this direction. So I'm going to take this as x-axis, and I'm going to write down my equations like this: F minus 2kx minus F plus 2kx, that is equal to mass into acceleration, and from here we can get minus 4kx equals ma, and that means I can write it a equals minus 4k upon m into x, and that reminds me of something in simple harmonic motion, that is a equals minus omega square x. So we got here omega equals under root 4k by m, and simply I can write omega equals 2 pi by time period, because I'm more concerned about time period, and that will be, well, that can be written something like that, and we can get the time period. We can reverse and square them, and we can simply get, that is t by 2 pi equal to under root m by 4k. That means we will get t square equals 4 pi square, simply square the thing, m by 4k. So this is the time period for longitudinal oscillation, like this. I would like to write this time period for longitudinal oscillation in this manner. I can write this. Now I would like to go for, I will simply collect this result, and I am going to discuss this transverse oscillation, and what can I do about its transverse oscillation. So you can see the picture here, and this picture, since A and B are fixed points, so for a small oscillations this picture will convert something like this, and this is the displacement of the ball from its equilibrium position, and this is the length of the spring. Suppose that I took the spring was already extended, and I took the extended length of the spring as L, and L is simply L0 plus delta L1 and nothing else, though I don't need this right now, so I'm not going to discuss it any further. This length is L by 2 and this length is also L by 2. Suppose that this angle is phi, so this angle will be also phi, and both the springs have a spring constants equal to 2k. So each one of them is exerting a force like 2k and increase in the length. I don't know how much in length, increase in the length. Let's call it delta L. So I'm going to write this force as 2k delta L simply, and the same force applied here. 2k delta L by 2 is the right thing. Calling it 2k delta L by 2 is the right thing, because the total length is L, so this is only the half of the length. So increase in L is delta L, then increase in L by 2 is delta L by 2. So I'm gonna write this, and the same force acts in this direction, and this is simply k delta L. That means 2 gets cancelled out, and one thing I need to take care that the x is quite small, so is phi. Phi is also very small, and these two forces, their resultant will be in this direction, and that will be 2k delta L sine phi. This is cos 90 minus phi, so this will be 2k delta L sine phi in this direction, so that I can write the equation so that I can write it equation as the force is 2k delta L sine phi. This is the force, and I need to write down its, and this is the force acting on the small ball or something, whatever it is, and that will be equal to mass into acceleration. Mass of the ball is supposed that m, and its acceleration I would like to write in terms of x. I can write x is the displacement, and x can be written here simply because x upon L by 2 is equal to tan phi here, and phi is quite small, so I can write it as x by 2L, so, or 2L by x equals phi. I can write like this, and so I can write here x equals phi L upon 2. So its acceleration I can write here m multiplied by x equals phi L by 2. So I can write it d2x by dt square as its acceleration. So I can write it ml by 2 d2 phi upon dt square, and I would like to put a minus sign here. There are obvious reason, you know why, because this force is a restoring force, and it will always act towards the equilibrium position, and phi increases in this direction, so a minus sign needs to be put here. And now what, since we wrote everything else, we can put this sine phi also equal to phi, because phi is quite small. So we got a relation like ml by 2 d2 phi upon dt square equals minus 2k delta L phi. That's right. And now we can write something the equation like d2 phi by dt square plus 4k delta L by ml phi, that will be equal to 0. And that reminds us that we can compare this equation with the equation of simple harmonic motion, and it will give us the angular frequency of this simple harmonic motion, transverse oscillation of this small ball, and that will be simply omega transverse, omega perpendicular, omega for transverse oscillation. And this I can see here 4k delta L by ml, and we can get time period for this oscillation, and I would like to write time period square equal to 4 pi square ml by 4k delta L. And you can see here L is nothing but L equals L naught plus delta L, and I would like to put and solve this problem as soon as possible. So I can write it, write this thing, T perpendicular, that is the time period for transverse oscillation, square equal to 4 pi square m by 4k, and put L equals L naught plus delta L by delta L, so that I can get something like 4 pi square m upon 4k 1 plus L naught by delta L, or something like that. This I got. And now we can say that we can find the ratio of periods, and ratio of periods like T half square, I would like to do it in terms of squares. T perpendicular, transverse, the time period for transverse oscillation, square by T parallel, that is time period for longitudinal oscillations, and I will make a ratio that will give me the values. I can find it, what 4 pi square m by 4k and 4 pi square m by 4k, and there was something in this problem, n1 n2, but they got different conditions. So I would like simply like it n square, and this n square will become simply 1 plus L naught by delta L, and guess you can find delta L by L naught from these equations and from this too, and we can get it 1 by n square minus 1, delta L by L naught. And we have something mentioned about delta x, and this delta x plus delta L1 was delta L2. That means we got another thing, that delta x equal to delta L2 minus delta L1, and we can get delta x by L naught as well. That will be equal to delta L2 by L naught minus delta L1 by L naught, and delta L by L naught, delta L2 by L naught, delta L by L naught is 1 by n square minus 1, and in the second case, when delta L2 was involved, the ratio was n2, so I can write it here 1 by n2 square minus 1 minus delta L1 by L naught as 1 by n1 square minus 1, and we can solve them, and we can get here n2 square minus 1 multiplied by n1 square minus 1, and that will be n1 square minus n2 square, something like delta x by delta L. Delta x by not delta x by delta L, delta x by L naught equal to this. And we can get the value of, since delta x is known, we can get the value of L naught, and n2, n1, everything is given. So we can get del L naught equal to n2 square minus 1 multiplied by n1 square minus 1 divided by n1 square minus n2 square multiplied by delta x, and you will get something like that it will be equal to 60 centimeter or like this. And accordingly we can get delta L1, that since delta L1 by L naught was given, so we can write here delta L1 equals L naught by n1 square minus 1, and you will get something like 4 centimeter. In the similar manner you will get delta L2, and that will be L naught minus n2 square minus 1, and that is something like 7.5 centimeter. Thank you for watching.